Okay, this is the second part of the lecture. We're going to talk about tangent plane to level surfaces. So now we're not going to take a flat metal surface anymore. Let's say our surface is represented by W equals 0, and we have a point, fixed point, and at that point, the partials are not all 0, and they're continuous. So let this curve lie in S. Okay, so we have this surface, and we have this curve line in the surface, and here's our point. And we want to get, that's the tangent line to that surface at P0. Okay, so the tangent, and this is the curve C. Is tangent to any curve that lies in S and contains the point P0. Okay, let R be a vector X, Y, Z, where they all depend on T. So we're going to take the derivative of W with respect to T. W is the surface, so we have the function with respect to X times dx dt plus function with respect to Y times dy dt plus function with respect to Z dz dt, and that derivative is going to be 0 because it's tangent to it. And then we have the partial. This is really f prime. This is g prime. And this is h prime. Okay, at the point P0, then we have del F, that's what this is, evaluated at P0, dotted with R prime at the point T0, and we have that equal to 0. Okay. Because, all right, this is equal to 0 because C lies on S, and that implies that f of x, y, z is a constant because it's a level surface. All right. Now this right here is the tangent vector to C at the point P0. Because if RT is this, then R at T0 is x0, y0, z0. It's the vector that points to that point. So when we draw this, then we have r prime of T0 along that tangent line. And what this says is when you take the dot product, this is so important right here because this says that the gradient f evaluated at P0 is orthogonal to every tangent line to S at that point. So it is a normal vector. This is perpendicular to the tangent vector. And the plane through point P0 with the normal vector gradient f evaluated at P0 is called the tangent plane. So let me go back and put in this picture, the gradient vector is going to be perpendicular to this, so this will be del f at P0. So we can go ahead and get the equation for the tangent plane. At the point, and that is fx evaluated at P0. This is using the tangent plane equation. So we can also get the symmetric equations of the normal line at the point P0. So we're going to use this to find the equation of the tangent plane, and this to find the equation of the normal line at that point P0. So let's do an example. Find the equation of the tangent plane and the normal line to this equation, or this surface, at the point 1, negative 2, 3. Okay, so first we take the partials. And we'll evaluate it at the point. So if x is 1, it's going to be 8. If y is negative 2, that's negative 36. And if z is 3, that's going to be 6. So using 1, equate the first equation, let's call this star 1 and this star 2, we're going to have the equation being 8x minus 1, we use the point there, minus 36y plus 2, we're using this point, plus 6z minus 3 equals 0. And that's going to turn out to be 8x minus 36y plus 6z minus 108. And we divide everything by 2 to simplify it. That's the equation of the tangent plane. Now, del F at P0 is the direction, and the point is 1, negative 2, 3, so we can get our symmetric equations for the normal line at the point. Well, let's do, okay, the symmetric equations will be this. If we get the parametric equations, we do 1 plus 8t minus 2 minus 36t and 3 plus 6t. So we can get either one where this comes from the direction and this comes from the point. Okay, so for a brief summary, del F gives us 1, the direction of the fastest rate of change or increase of F, and 2, it's orthogonal to the level curve that passes through P. So there's a lot of information here, and you can look at some of the example homework problems to work some of these problems.